Here we go. Okay, so page 115 again. Your homework for this section. This is the multiple choice for part 6. Okay, we're coming down here to the end. Part 6, page 126 to 137 will be your homework. So with that, I want to go over the tests that we have covered this year with inference. One proportion z-test and one proportion z-interval. And the two proportion z-tests and the two proportion z-interval, that is when the language that you would use in your conclusion is, there is a significant difference in the two proportions, or there's not a significant difference, it's about the difference. Then we have one means. Recall that means are t-tests. T-tests. And one mean t-interval. So we're going to discuss what is the thing that makes the means need to be t-tests and t-intervals. You what? You don't have the population standard deviation. So t is used because you have no sigma. You have no sigma, which is population standard deviation. So t is used because you have no sigma. You just have the sample standard deviation. All right. Then, of course, you could have two means, t-test and two means t-interval. And when it's two means, so let's talk about this language, because if you remember, we had a lesson about difference in averages and average of differences. So let's have a little discussion about that. Difference in averages is this difference between two averages, so you do a two-mean t-test or a two-mean t-interval. But what happens if I do a matched pair? Think of how a matched pair is organized. You have like before and after data. If I have before and after data, then I would probably solve it like this. I would put one set of data in list 1, the other set of data in list 2. I would subtract, and I would get my list 3. And all I am interested in is list 3. So because that's the only thing I'm interested in, I am just going to average this list 3, which are the differences. I'm going to average the list of differences. Okay? So let's remember that language. You can find a difference in two means, or you can find the average of the differences. Difference in two means or the average of the differences, okay? So you'll want to use that proper language when you're talking. So that's what this section is about. Moving on. So this is some good inference stuff that I'm going to let you can just read this on your own, because we're going to actually talk about it. We're going to cover it in the songs, okay, and go through it with that. Let's see here. Okay, so in this, they have got ways to interpret confidence interval and confidence level, and we're going to do that with our songs, okay? So in a few minutes, we're going to talk through the words of our songs. Now, here on the next page, we've already discussed how for a t-test or a t-interval, it's because you do not have the population standard deviation. All you have is the sample standard deviation that causes extra variability, so that is the reason that you use t-distributions. Now, if you look at this page just goes through all of the tests that we're going to do, but I want you to look at these two ones that are closed, or that are marked out. They're interesting. They are marked out because this is actually a mean test that would use z-scores. So that's interesting. Not going to happen very often at all, because in order for that to happen, you would have to know sigma, the standard deviation of the population. Same thing with a two-mean z-test, and I think there is one on your multiple choices that you will be doing. And there is a sigma has to be known. All right, but those happen very rarely. That's why mean tests are predominantly t-tests. Okay, moving on to, that's all the tests. This is a page that I'm not going to go over with you. It is a flow chart of how to know what test to use. So if you have trouble figuring out if it's one too simple, if you know things, whatever, you don't know things, then you can look at that. And let's now go on to this next page here. This top section talks about variability, and I think you know that when you've got your low variability and your high variability bias, we haven't really talked much about. So we'll move on to this. We now also need to discuss type 1, type 2 errors and power. Okay, so I want you to write down this remember this picture thing that we use to remember stuff? So write that down. So type 1 error is the same size as alpha. Type 2 error is the same size as beta. You know that your N affects your standard deviation. And these are all ways that power increase. Okay? Now, the alpha is in blue and the N is in blue. The reason those are targeted or set aside differently is because as a researcher, you have control of those two items. Those are the two items that you can say, hey, I want to do this research and I want to change power. Well, then you can change N or change alpha. Alpha and N are the two things you can control. Now, so let me explain how this works. Say N is increasing. Well, if N is increasing, then that means that your power is increasing and that your type 2 error is decreasing. N actually doesn't necessarily change type 1 error. Alpha has to be changed in order to change that. Okay, now you could do the opposite of this. You could do this picture where your power decreases. So all it is that your power decreases, so your arrows are going in the opposite direction. Okay, so your arrows are going in the opposite direction. Okay, and then when we look at the songs, we'll recall the definitions of type 1 and type 2 error. Now, let's take a look at your formula chart. So everybody pull that out because you're going to want to write on that or at least take a look at that. If we see, here is the front where we've been dealing with on your formula chart. Okay. We've pretty much made our way through that. So we are to the back where inference is. We are to inferential statistics. So on the back, we are going to focus today on this part on confidence intervals. All right, so let's take a look at this. Let's recall how a confidence interval works. Remember that a confidence interval, what is a confidence interval? What does a confidence interval do for you? It's a range, it's an estimate for something that you are trying to find, like the proportion of water on the globe. So you collect a sample and you make and you're making an estimate with this range. Okay. So please keep in mind that here's what physically an interval looks like. You have your statistic right here in the center. That is your statistic. That's your sample proportion or your sample mean or whatever it is you're finding. And then you have plus or minus. Do you see this part behind the plus or minus in the formula? That is your margin of error. So you have your plus, your margin of error up, and minus your margin of error down. Okay? Plus your margin of error up and minus your margin of error down. So you need to understand that physical situation there. All right, now, critical value. This critical value is your Z star or your T star. And that critical value is based on how confident they tell you to be. If they tell you to be 95% confident, then you wouldn't have 95% in the middle, and you would do inverse norm of one tail, which if you're 95% confident, how much would be in one tail? 0.025. Good. Now, recall that if you do inverse T, that would be inverse T comma one tail. That's if you're doing an estimate for a mean, comma, degrees of freedom. Recall that inverse t is one-tail, comma, degrees of freedom, because when you do t-tests, you must include the df. Which for a simple proportion or mean, how do you do df? N minus 1. N minus 1. Okay. Now, one of the common things that you will be asked to do is to find a sample size to meet particular criteria. So I have an example, a rough example sketched up here. So they'll say, hey, you're a researcher. What sample size do you need to accomplish in order to be, here's my example, 95% confident and have a margin of error of 0.04? Okay, so they say that to you, and you have to figure out how to compute that. Do you recall? How would I do that? Good. Set your margin of error equal to that part of the formula. Critical value times standard deviation. See, I am setting the margin of error equal to this part of the formula. Okay, so then I would know, let's say if I'm doing this particular situation, then I know that I've got my critical value, inverse norm of one tail. So see, there's my margin of error would equal inverse norm of one tail. This happens mostly when you have proportions, not means. So there's my proportion situation. Why do I have that N highlighted? Because that's what I'm trying to find. I'm trying to find sample size. And I should have every other piece of data there. Well, let's fill in the blanks. We know margin of error is told to me to be 0.04. We know inverse norm of 95% confidence will be inverse norm of one tail, which is 0.025. Now, how about this P? The best you can do is use true P, but if you don't have that, then you can just use P hat. Worst case scenario is those don't jive. Please don't cry. Please don't cry. Just use 0.5. So that's what I had in this particular case. So I filled in my margin of error, my inverse norm of one tail. I didn't have P or P hat, so I used 0.5. Look at the only variable unknown there. N is the only unknown. Then you do algebra to solve that, and I'm not helping you there. You're seniors or high-performing others, so hopefully you can do that yourself. Okay? All right. Let's see. Now, one other thing, okay, that I wanted to make you recall. When we had the proportion of water on the globe, let's say this is the true P of proportion on the globe. Do you recall when you guys made your little intervals? You all did your example, and you all got your own P hat, and you all made your own interval. Okay? So tell me about these intervals. Are they all going to contain the true proportion of water on the globe? No. In fact, if these are 95% confidence intervals, what proportion of all intervals, 95% confidence intervals made, what proportion of all intervals made should contain this true P? Okay, good. If these are 95% confidence intervals, then 95% of all of those intervals should contain that true P. So, could you make an interval that doesn't contain true P? Yes, you could. You could have made this P hat, which made an interval that doesn't capture your true P. All right. Let's go to the songs now and kind of talk through those. You know the central limit theorem, we've already done that, and the assumption song, we know that. Okay, type 1 error. Let's review type 1 error. So, if the null is really true, but we get a sample that causes us to reject the null, that's a type 1 error. So the null is true, but our sample misleads us and we reject it. The meme that I've shown for that is Ryan Gosling. He says, "Hey girl, I shouldn't have rejected you." Okay? He's making a type 1 error. Okay? No, it was not. No, it wasn't. Mark Wahlberg meme said, "Sup, increase your sample size. More power to you." Aha. Increase your sample size. More power to you. Yeah, that's Mark Wahlberg. I know my memes. Okay? All right. Next. Type 2 error. Oh, type 2 error. You failed to reject a false null hypothesis. Type 2 error. Type 2 error. So the null is false, but we failed to reject it. We don't reject it, and we should have. And so remember the meme was that silly face, and he goes, "Why you no reject the null? Why you no reject the null?" Okay, you were supposed to. All right, power. Power is the probability to reject the null if it's false indeed. Okay, so we want to reject it if it's false. Okay, and so power, we want power because we want to reject the null hypothesis if it is false. We want to reject O.J. Simpson's innocence if indeed he is guilty. Okay, all right. You know p-value is low, HO has to go, and you know Star Spangled Banner is significant, statistically significant. Okay, here is the song for confidence level, and that is that one that we just discussed previously where you say 95% of all of those 95% confidence intervals contain the true parameter. So let's say 95%, 95%. Of all 95%, 95%, 95% of all of these confidence intervals, intervals of confidence, they contain this true parameter of interest, which is the proportion of water on the globe in this case. Parameter. Oh, whoa, whoa, whoa. What happens if it's 98%? Then what does that mean? 98% of all of the 98% intervals, confidence intervals. Why are more of them capturing the true proportion? What do you tell me about the quality of a 98% confidence interval? It's wider. 98% confidence is wider. Okay, you know your brown-eyed girl p-value? The p-value is the probability dun, 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 of getting this sample or something more extreme if the null is true. All right? We don't do this assumption song because it's slow and boring. And this, what proportion to use to find n is the one that SoundCloud won't let me put up there because they say I'm jipping off some copyright. So the best it can be is if you use true p. That you can just use p hat. The worst case scenario is those don't jive. Please don't cry, just use 0.5. So who's got a mean test? Who's got a mean test? T, not Z. Sample standard deviation. See, it's in the song. Sample standard deviation. T, not who's got a mean test. Must include the DF. T, not Z. All right. So there you go. That's all your concepts. Don't forget to follow me on SoundCloud at Mary Mac, okay? And I'll try and see if I can't fix it so that all the other ones that aren't on there yet are on there. So there you go. Okay. Please subscribe, right? Is that what you say on YouTube? Okay. So your homework is pages 126 to 137. Yep, Mary Mac. Yep, here I am, Mary Mac.